Hi, everybody. Welcome. I'll just give it a couple more minutes before we get going. Thanks for joining in.
Hello, Birgit. Hello, everyone.
All right. Since a lot of people are here, I'll just get going. I think people will trickle in and out. So welcome everyone. This is a webinar hosted by Angelos and myself from Superbio. We're going to talk about ParaSurf, what is this new AI model that Angelos and his co-authors have developed for predicting antibody binding sites using deep learning. And I'll talk to you about agenda. Very brief introduction, a few minutes to Superbio. Then we'll have the research presentation by Angelos. Then we're going to spend a few minutes, maybe 5 to 10 minutes for Q&A. And please feel free to type in your questions into the chat during my talk or during Angelos's talk. And finally, we'll have just a few minutes of closing remarks and we'll wrap up in about 45 minutes. So just to start off, what Superbio is, essentially we're a software company that is looking to accelerate research with generative AI. What we're building is this intuitive and collaborative AI platform specifically built for R&D. We provide easy and instant access to best-in-class AI models. It eliminates the need for you to build IT infrastructure to be able to run these AI models. And not only do we serve hundreds of AI models specialized in biology applications, we also have built the software around the models that we serve that facilitates collaboration and allows teams to work together under one workspace. And finally, often organizations would like to take an existing model and customize it so we allow you to fine tune it through our product or services at times. So not only, as I mentioned, the platform comes with 100 AI models, really easy to use graphical user interface and APIs. We also have these collaborative features that's built in, a data hub that allows you to manage your data and bring your own tools capability. If you're working as a team and you would like, as a computationalist, serve your models, serve your tools to experimentalists, we allow you to deploy your own tools privately and take advantage of all these key features that you see on the platform just for your own tools. Before I show you what the platform looks like, these are just some of the use cases that are most relevant, most highlighted, what gets the most traction on our platform, whether that's using Baker Lab Institute for Protein Design models to do protein DNA modeling or designing protein binders, or using state-of-the-art diff.L to model molecular docking, running literature review using a model that we have developed ourselves called SearchBio, or running some single-cell analyses using the state-of-the-art transformer model, SCGPT. Today, the platform looks like this. It's just like an app store. You're sort of presented with a lot of different AI models presented as cards. If you're interested, you can type in your specific use case that will bring back all the models relevant to protein design, for example. If you're interested in RF diffusion and want to run it, you can click on the open. Um, and here you basically have the ability to upload your own data to run this model. If you want to read about it, we have this about section, example use cases, limitations, some information. And you can use our demo data if you don't have any data, select some parameters. And if you don't know what these parameters are, we usually provide really helpful tooltips for you to set them up and then run this on the Superbio infrastructure. So this is graphical user interface. We have the same capability over APIs as well if you're interested. Once that is done, you can click on the results. You can view these results through the platform. share your results with the entire organization that you're under, and you can sort of leave some comments here. I'll talk a bit more about it at the end, but without further ado, I'll just like to introduce you to Angelos and talk about ParaSurf for predicting antibody binding sites with AI. So, Angelos, thank you so much for agreeing to do this, and I'll pass it to you to continue.
Yeah, thank you, Berge, for the wonderful introduction. Hello, everyone. I will share my screen. I have a presentation ready. Okay, how do I move this? Okay, hope everyone can see.
Yes.
Okay, perfect. As Berge said, I'm Angelos. I'm a research associate at CERT, at the Visual Computing Lab. I'm also doing my PhD. I'm a PhD candidate at UPM and in Madrid. And this work is in collaboration with INAV, the Institute of Applied Biosciences. I think here with us we have a co-author, Anastasia. The work is called ParaSurf, a surface-based deep learning approach for power-to-quantum interaction prediction. This is the outline of how the presentation will go. First, I will try to familiarize you with what an antibody is, what an antigen is, what's the problem that we are trying to solve, our methodology. We will show the results, some challenges that we mitigated, some contributions, our future work, and then we will proceed to a demo in the Superbio app, and then we will answer some questions. Okay, so this is the introduction. We all know that B cells are essential. In advance, I want to apologize if I make any mistake regarding the bio stuff because I'm not so familiar, but I will try. We know B cells are essential in our immune system. They mature in the bone marrow and then produce antibodies. And the antibodies are these Y-shaped proteins that consist of two identical arms, and they consist of a heavy and a light chain. These antibodies bind to some foreign antigens like bacteria, and then they activate some immune response to cure these diseases. In the bottom right image, we can see the main regions of an antibody. We have the constant region, which we do not care so much about regarding our computational methods because it doesn't change much. We're most concerned about the Fab domain and the variable region. The variable region is the most important part because this is the part that changes when the antibody tries to interact with the antigen. However, in a B cell, for some genetic reason, which I'm not familiar with, becomes malignant. This can cause the B cell to overpopulate, to resist the cell death. It has a resistance to apoptosis. This can cause cancer. A very well known is the CLL, chronic lymphocytic leukemia. This abnormal B cell then produce abnormal antibodies. We can see on the top right image, let's say an abnormal B cell that has an abnormal antibody interacts with a self-antigen, an antigen from our body, and then it produces a signal, a response to our body that can cause harm. On the bottom of this slide, we can see the 3D structure of an antibody, how an antibody looks like in its whole form. We see this Y-shaped, as I told you before. But what we most care about is the Fab region. The Fab region is either the right or the left arm of the antibody. This is how the structure looks like. Here is the surface representation, and here is the chain representation. It consists of both heavy and the light chain. On the left image, we can see again the total structure here with the antigen. And here the zoomed in version of the variable region. It has the complementary determining regions, starting from 1 to 3, with the most variable one being the H3 and L3. These are the loops from the antibody that change the most when they interact with an antigen. Hope you got an idea of how these complexes look like. Now, I will try to define the problem, what we're trying to solve. Uh, we're trying to find, to classify which residues from the antibody bind to a specific antigen, to its corresponding antigen. The rule that we follow here, and all the literature, of course, is that if any heavy atom from the antibody, a heavy atom is a non-hydrogen atom, for example, a carbon oxide or I don't know, is below 4.5 Armstrong from any heavy antigen atom. So this is the basic rule. We have three prominent datasets, three prominent antibody-antigen datasets. One is PICAM, paragraph expanded, and the MIPE dataset. We can see here how the splitting is done. The splitting is not done randomly. It has some criteria. They mostly use the SD-HIT clustering tool, which is based on the sequence similarity. We want the maximum pairway sequence identity to be below 95%. And of course, we want only complexes that are paired with a heavy and light chain. Below, again on this slide, we are seeing the ground truth. Some samples of from our dataset. We have the BCR, B cell receptor or antibody, the antigen, and the ground truth. But as I said before, we care about the residues. Here I show you the surface for context purposes. I will proceed with the methodology now. Each sample from our dataset looks like this. We have a complex of antibody and an antigen. Our first work is to remove water ions and ligands from the structure to have a clear view. As we said before, we care about the heavy atoms. Then the step two is to perform a sanity check. This is to throw away any junk files that we may have in our dataset. Any complex that does not obey to the 4.5 Euclidean distance rule is thrown away from our dataset. Then what we do is we take the antibody structure, and with a tool like DMS, we produce the solvent accessible surface area. The DMS represents the van der Waals molecular surface of the antibody. And here, each atom gets populated by the surface points. Then, having the surface structure, we perform a balance sampling. Here, we take what we did is take 800 samples, positive samples, and 800 negative samples. This number of positive samples is as much closer as we can get to the antigen. And then we randomly take 800 surface points from the other antibody structure. Then from each surface point, now we have a total of 1,600. We create a voxel grid of 41 by 41 by 41 by 22 voxel grid. This is not done randomly. The 41 was suggested by the DIPS paper, I think. Is for general protein-to-protein interaction methods, not protein to ligands. For protein to ligands, I think it was 16, the grid. So in total, till now, we have this step. We have our complex. We clean it. We take the surface, and we take the ground truth and the non-binding surface points in order to have a balanced data set, because we need to train it at the end. Now, what this cube, this grid comprises of? Here, I forgot to say before, the label 1 means, of course, that this surface point is binding, is located below 4.5 Armstrong from the antigen. We mostly care now about this 22 feature vector, what it comprises, what is its contents. Here we have 18 chemical features and 2 electrostatic phosphate features, among, of course, with the atom radius. The 18 chemical features come from the Open Bubble software. It has the 9 atom classes. These are carbon, pyridium, or I don't remember if it's metal, etc. It has hybridization, heavy valence, if it's an aroma, ring, etc. And from the PDB to PQR tool, we take two electrostatic force fields, the amber and the charm, that help us define some the force fields that happen in these surface points within the antigen, antigen. Sorry. Okay, so now we have our dataset ready for training. As you can see, these voxel grids are our input to the model, of course, in the batch form. We can see here these voxels, 0 or 1, pass through our hybrid neural network. It comprises of, it's a simple architecture, 3D resonant, with a transformer block at the end. And the output is a value between 0 and 1. It's a 3D binary classification task. Some training details here. We have of course, binary cross-entropy loss. The batch size 65. We use Adam optimizer. We have a scheduler. And all the experiments were done in 3090 RTX GPU. You can see here also the input at the inference point. We have only the antibody. Our model is antigen agnostic. When the model is trained, we do not care about the antigen. We just want the antibody. And the output of the model is that it highlights the binding residues. Now we will move forward to how do we validate the results? Because as I told you before, we care about the residues. And here I show you about the surface points. So how do we go from the surface points to the residues? It's very simple. Actually,
Angelos, just to jump in, by the way, you have a question on the chat, if you want to.
yeah, sorry. I have everything closed here. How do you determine which 800 positive surface points to use? Yeah, probably I was not clear about that. The 800 positive surface points are the points that are as closer as we can get to the antigen. And then for the negative surface points, we just randomly go to the whole antibody structure. And of course, the 800 is not randomly. We performed many experiments, and we saw that the 800 is the best fit. I think I covered you. I have the chat ready, so I'm able to see the questions now. But now, how do we go from the surface points to the residue level prediction? It's actually quite simple. We follow this equation here. Let's present an example here. We have glycine, I'm not so sure, that clearly belongs to this residue, belongs to the binding site. It belongs to the M chain. I think probably it's the heavy chain because it's the biggest one. And it's the 97th residue from this chain. Now we want to say if this residue, this yellow one, is 0 or 1 for the model. We will hypothesize that this residue has 10 atoms. Now with our tool, the DMS tool that presents the surface, from these 10 atoms, we go to 100 surface points. Now from each surface point, we produce this voxel grid, as we showed you before. And then we get the predicted score, 0 or 1, for this voxel grid. Then to decide if this residue belongs to the binding site or not, we follow this equation. We take the predicted score for each of from surface points 1 to 100, and we take the maximum prediction score. If the score is above 0.5 threshold, then we classify this as binding. Of course, this happens to every residue. Here we have a tyrosine, which we hope the model predicts it as 0. Yeah. This is the model. It's actually simple idea. Now we proceed to the results. How do we validate our model? The most important metrics here in general, protein-to-protein interaction tasks, binding site prediction tasks, it's AUC, ROC. But because we're dealing with antibody-antigen structures, the most important is AUC precision. This happens because this task suffers from class imbalance. This is one thing that we managed to mitigate. As you can see, the binding sites from the antibody are a class minority, and the total number of residues are zero. That's why we did the balance sampling to tackle this issue. And of course, the AUC-ROC, it's a classic discriminative ability of the model to decide if an atom surface point is binding or non-binding. Below from the slide, we can see some qualitative results. Our model is able to determine if a binding site, if a binding residue belongs to the binding site across the entire Fab domain, which some previous state-of-the-art couldn't do. And of course, if we have the Fab domain, we can take decisions about the variable domain and the complementarity determining regions also. Here, the best values are shown in red. We also saw the surface, the surface from these residues. And again, on the right, we can see the complex. Again, I have to point out that the input to our model is only the antibody. Here, the antigen is given for context reasons, but we will see them on the demo later also. Here are our results on the three benchmarks. You can see these values also on the paper. We achieved state-of-the-art performance across these three datasets and across these state-of-the-arts. Of course, you can see also our results on the papers with code by date also on these three datasets. Some more in detailed results are that we also achieve state-of-the-art results on the most variable regions. As I said before, it's the three loops, the SDR3 loops for both the heavy and the light chain. You can see the results L3, H3. And of course, as I told you before, we were able to generalize across the entire Fab region, not only the SDR loops or the FV domain. As you can see, the previous state-of-the-art paragraph here, we performed a double score on the framework region because what we did is perform only predictions here on the SDR region and then just place the value 0 to the other residues. Here are also some other results. Again, the input to our model is an antibody. We predict the binding site. Here you can see an overlapping of the ground truth binding site and the binding site that we found out is binding. Some more results. Okay, we will see this later in the demo. These are the PDB codes that you can search from the protein data bank online. Now, another case is that on the wet lab, scientists can only have information about only one chain. They are unable to have the whole antibody structure. So what happens then? The previous state-of-the-art paragraph also did some experiments there, and we achieved, again here, state-of-the-art results when having solely one chain, either only the heavy chain or either only the light chain. Here we performed experiments on all the three datasets by keeping only one chain as the ground truth and experiment with this. Here you can see some results. This is the binding site. This is the antigen for both heavy and light chain. The challenge that we mitigated, again, here is that we were able to generalize across the entire Fab domain. Here you don't have to give a hard code 0 on the other residues that we think that do not belong to the binding site. What paragraph did was give the value 0 outside the SDR plus minus 2 region. They didn't miss much of residues, but they did miss some with this assumption. And of course, we provided the state-of-the-art result on the R3 groups and on the framework region. The main contributions of our work is that we were able to mitigate the class imbalance, the inherent class imbalance issue on the antibody-antigen task, binding site prediction task, sorry, by performing a balance sampling. We integrated the geometrical, chemical, and electrostatic features. We used a hybrid model to capture both local and global context. We were able to generalize across the entire fab domain. We produced state-of-the-art results on the three prominent benchmarks on the SDR3 loops. Our model is antigen agnostic. Again, we do not have the model does not have any information about the antigen when it performs its prediction. And of course, it's effective on when you have solely one chain. Some future work that we are planning to do is that we are trying now to integrate ParaSurf in protein-to-protein docking methods like DiffDock PP. Of course, this will guide these methods to directly dock the antigen there on this side rather than performing an exhaustive search on the entire antibody structure. And of course, where the bioinformatics is leading is the antibody and antigen design. We believe that ParaSurf will play a vital role in validating the results in silico. And of course, we believe that it can also guide the antigen generation on specific site. Say that we have an antibody and we want to generate an antigen that will bind there. We now know exactly where do we want to bind, and then with some techniques, protein MPNN, some hallucinations starting from the AlphaFold, iteratively we can find the antigen we want. Yeah, thank you. You can find our paper on bioinformatics. Also, we have uploaded the GitHub code. All the weights are available. Everything is ready to use. We have a space on the Hugging Face. And of course, we will now see an example on Superbio app. Berke, can I proceed to the demo? Or
Yeah, please go ahead.
okay. Okay, here we go. Okay, I have some. I will open Chimera X. It's a visualization tool where we can see everything if it opens. Okay. Okay, so what I have done here is have some test PDBs. For example, we can try the PDB complex with the code 1FJ1. Here we can see. Of course, you can, if you type this PDB code online, I don't know if you will get this exact structure. You may get, actually, we can see it. 1FJ1. Yeah, you will get this complex, but it's very easy to parse this total protein, so you can get exactly this. It's a dimer. I'm not so sure. I don't remember how it's called. Anyway, we just as I told you before, we want this structure. We have the heavy and the light chain in the antigen. So we want to pass on Superbio the receptor, only the antibody. We use these weights because it is on the biggest data set. We suggest using this is the mesh, this is the surface representation. We suggest you use 0.1 for fast results, run on GPU. And now we wait. It takes about 10 minutes on Superbio app, but till it's done, we can see a previous example. I think there's a question. I'm not familiar with the paragraph method, but in your opinion, what makes the ParaSurf algorithm better than paragraph? Yeah, I think, Kevin, what makes ParaSurf better is is the balance sampling thing that we did. I think paragraph is dealing with graphs. They focus mainly on the SDR region. What is the SDR region? Again, we can show it here. Where is it? Here. They focus mainly on the SDR region, and we're focused on the entire fab domain because they're dealing with graphs. I think they mainly focus on this region, and when they're trying to generalize the result on the entire fab domain, they get poor evaluation results. I think this balance sampling did the trick for us. And of course, we integrated these features, and it was not done at once. We tried feature by feature, and we figured out that these are the best fit. Now, what else? I'm not so sure because the architecture is quite simple. We did not do any magic there. Yeah. Okay, where was I? Berke, we can see a previous example here before this is ready.
Yeah, that makes sense. That's how I do it as well.
Okay, perfect. Okay, this is from the 3GI9 receptor. We can download the output files. Right here. Okay, these are the results that you will get from each antibody. Okay, we will hide this now. Go away. Okay, these are 3GI9. Okay, I have here the 3GI9. No, yeah. Okay, so here is the initial complex from the 3GI9. Again, you can parse this result from the PDB. And now we will pass the predictions from the ParaSurf. Downloads. I will throw it there. Oh. Excuse me. Okay. So what are the predictions? Here we have, we will hide the receptors from now. And this is the predicted receptor. You can see here, which is that is the pred, right? Yeah, this is the prediction of our model. And we highlight the binding regions. If you go to the B factor, we just pass the PDB, the predictions to the last column of the PDB. So you press the B factor here. I did something wrong. If you press the B factor here, you will see the binding residues. This is the finally this is the output of our model. Here you can see is classified on the residue level because this is how the other state of the art did the work. But as I told you before, we went to the residue level starting from the surface points. So that means that we have predicted scores for each point. That's why our model also predicts a per atom prediction. Again, if we go to the B factor, you can see here is actually more accurate if we go per atom. You can see the red is closely to the antigen. And lastly, the last output that we have is the pocket, which is the surface representation of the binding site. If we go and show the results, you can see this is the surface that the antigen binds to. The surface here is quite small because we chose zero point 0.1 mesh. If you chose bigger, you will get a bigger cover here. I see a question. Does your approach only work for classical antibodies, or would it also, with modification, be able to support prediction for nanobodies? Great question, Jonas. It also supports nanobodies, yeah. Do you have any in mind right now? We can try one. I don't remember. Yeah, no, but yeah, we do not want, we do not need the entire Fab domain. You have only what is a nanobody? I think the nanobody is that we do not care about this low belt. We only care about this domain, the variable domain. Or am I wrong?
Well, and it's not heavy chain light chain pairing, right? It only consists of, if you want, a heavy chain only.
Okay. Yeah. As I showed in the presentation, we can run these examples. Yeah, when having solely one chain. We also have on the GitHub. We also have the weights when you're having only heavy chain or only light chain.
Right.
Yeah, we can actually go. Yeah, if you go here to the weights, our models are hosted here. We have all the datasets, and for the paragraph expanded, we have if you have only one chain, we have the weights that you can download. Okay, let's see how we are doing here. Okay. We can see also this example. Anybody has any questions for this?
Yeah, feel free to type in questions or just unmute yourself and ask
Mhm.
questions if there are any.
In the meantime, I will go to to this one. We can show also this one. It's a 3i50.
I'll say that you have great graphics to go along with your illustrations here.
Thank you. Thank you, Kevin.
All right, seems like there are no more questions. Is there more that you want to show, Anios? Or are you done with the
No, I will just
presentation?
iterate with some examples here on some visualization, but I saw one example. I don't know.
Sure, sure, yeah,
Uh,
go for it. Go for it, go for
okay. So our next example is this. Again, we have this complex. I have the results here. Okay. So for this complex, again, we will proceed. We will have the receptor. This is the residue prediction. We'll have the pocket also. If we press the B factor, again, we can see the output of the model. You can see the level of detail. But as I told you before, we can also have per atom prediction, which is even more detailed. Because if you remember the previous rule, if you have solely one atom that is above 0.5 threshold, the whole residue is classified as binding. So that's why there are more reds on the per residue. And of course, we have the atom. We can show it here. Again, you can see how it encapsulates the antigen. And this is why I believe it can guide the antigen generation. For example, you can go here and give some protein MPNN, some alpha-fold hallucinations, and step by step produce an antigen like this that will hopefully bind on a wet lab experiment. Yeah, hopefully this is done. Oh, still running. Yeah, very good. I think we are covered with
Okay,
the visualization.
perfect, awesome. Well, thank you so much, Angos. I'll just what I'll do for everyone is I'll this is we're being recording this, so we'll share this afterwards. And just as final closing remarks, um about Superbio and about the presentation and sort of how to stay involved. Of course, if you use the Superbio platform, your data is handled with high security standards. If you're on a team account, we delete your data after a certain amount of days. And usually when we work with a team, we kind of assign an AI team that helps with everything, data, performance, making sure that the model and data that goes into this platform is safe, secure, and high performing. And if you like what you saw today, if you want to see more webinars like Angelus's, I will send out a follow-up email. Just feel free to hit reply, and we can provide you 1 month of free boost, which gives you sort of a subscription for 20 hours of GPU runtime for free. You can also join our Slack community. I'll send you an invitation as well, and let us know if you're interested in exploring team features and how to use Superbio as a team. So we can just hop on a call and talk you through how we can be helpful. So I'll stop there. If you are interested in learning more and asking questions to me, to Angelos, feel free to reach out to us anytime. And thank you so much for joining today. And thank you so much, Angelos, for hosting and presenting your work with ParaSurf. It is
My
quite
pleasure.
exciting. You have the access through the GitHub, the paper, also through the Superbio platform. Thanks, everyone. Have a great rest of your Thursday. Thank you so much for joining. And I'll hopefully see you soon. Bye bye.
Goodbye, everyone.